Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, Spectrum Monitoring Techniques Capturing Unknown RF Signals, presented by Anritsu. Our presenter today is Tom Elliott, Senior Product Manager at Anritsu. And helping out with the Q&A at the end will be Eric Hokinson, Senior Product Manager at Anritsu. At this time, I'd like to pass the presentation over to Tom.
Hi, this is Tom Elliott. Welcome to Spectrum Monitoring Techniques by Anritsu. With me today is Eric Hokinson, who will be dealing with the questions, and I'll be doing the discussion during the slides. So there's a lot of different reasons to monitor spectrums, and let's talk a little bit about them. Everyone has their own reasons for monitoring spectrums, but some of the reasons would include people involved in spectrum clearing. They want to see what's out there. Regulators, particularly in Europe, pay a lot of attention to who's using what frequencies. There's white space projects and spectrum utilization research. There's even people chasing illicit transmissions. This could be either a pirate radio or just the old type James Bond type bugs. People that are interested in interference monitoring and characterization come high on the list of people that want to monitor our spectrum. In particular, the 4G LTE signals have some cell edge and co-channel interference issues and are particularly sensitive to interference compared to some of the earlier technologies. Now, traditionally, particularly in the cellular area, capacity has been a big deal. Frankly, they've shot for coverage over capacity. You remember the old coverage maps and advertisements with people walking around with coverage maps over their heads. That's all how much territory we cover, sort of a thing. Now with the move to 4G, there's been a new focus on capacity. You can see a stadium like this. What happens when 50,000 people want to stream, replay that last fourth down play?
Okay, so spectrum monitoring tasks revolve around observe, observe and record, and observe, record, and compare. Observe is simple. If you go to a place and find the signal, you're in good shape. If you go to some place to observe a signal and it's not there when you are, it gets a little more complicated. Or if behavior over time is interested, it becomes a little more complicated. And then there's observe, record, and compare task. This is part of a systemic spectrum monitoring program where you might have been there a month ago and you're again this month and you want to see what's changed in the meantime, what signals are new, what signals are missing, and you want to see if there's any signal change that correlates to another event. The signals of interest when we're spectrum monitoring include accidental interference of a variety of types, illicit transmissions, intentional interference, or even simply taking baselines. Setting up to monitor is where we get into the meat of the presentation. Okay, so the first thing we need to do, of course, if we're going to spectrum monitor, is choose a frequency range, and this is often defined by our task. For instance, if we're a cellular operator looking for uplink interference, we already know our uplink frequency range. After we've chosen our uplink frequency, the span we're going to monitor is the next question. There's a number of trade-offs here with choosing a span, and unfortunately you can't get one span that does everything all the time. So the issue here is resolution bandwidth is coupled to span normally. A resolution bandwidth, quite straightforward, it is the resolution you have on the frequency axis. If you look at the screenshot I have here in the upper left corner, you can see the signal in the center and on the left. They show that rather parabolic looking signal. That's not actually the shape of the signal. It's the accurate power and it's the accurate frequency, but it's not the shape of the signal. Rather, it's the shape of the instrument's resolution bandwidth filter. If you look over on the left side of the screen, you'll see a wider signal. Now you're starting to see the true shape of that wider band signal. And this is the difference I'm talking about. So if you want to see the shape of those narrower signals, you either need to go to a narrower resolution bandwidth or need to span down. Finding one all-purpose span, many times you can't do it. The trade-offs are this, okay? The resolution bandwidth affects the signal shape you see, how well you can see the signal shape. It affects the trace update rate. Then the better resolution you have, the slower the update rate is. And it affects the noise floor. Lowering the resolution bandwidth by some 10 times will lower the noise floor by some 10 dB and allow you to see smaller signals. Then there's the trace point count. There's something like 551 points per trace. That's about as many pixels as we have on the display. If you're trying to see more channels than that in one sweep, perhaps you need to choose a series of narrower sweeps. So we've talked about resolution, bandwidth, and span. Let's talk about trace modes for a little bit. If you take a look at the upper picture, you can see a blue, a yellow, and a green trace. We're looking at a Wi-Fi signal here, okay? The yellow trace is the normal trace, and the normal trace changes as the Wi-Fi signal comes and goes, because that's a bursty type signal. And you can see the normal trace is coming along there, fat and happy, just about on its baseline, about the center of the screen. Then suddenly the Wi-Fi signal turns on. You see a sharp jump in the trace, and then you see it following the envelope of the signal off to the right. The green trace shows everywhere the yellow trace has ever gone. That's the max hold trace, and this gives you the envelope shape for the Wi-Fi signal. The blue trace shows everywhere that the yellow trace does not go. It shows how low things go. And as you'd expect, since this Wi-Fi signal is turning on and off, it's mostly a flat line. But if you look at the very center of that blue trace, right on the center, you'll see a small signal that's coming up. That signal is always there. It's normally masked by the Wi-Fi signal, but it is always present. And that's what the blue trace, the min-hold trace, is useful for. Now, another way to get the noise floor a little lower is by trace averaging. In the lower screenshot, we've shifted to the cell bands, working in a cellular downlink band, and we've turned trace averaging on. Over the period of time it takes to collect 100 traces, the yellow trace has been averaged, and you can see how much less noise there is on that trace than there is on the upper screen. However, it took 100 traces to get that. There's an alternative to trace averaging that is sometimes useful. It's not really a trace mode, but it's the video filter. The video filter reduces noise. It also reduces fast-changing signals, so it's not a panacea here. But it works with digital signals. Trace averaging will sometimes reduce digital signals if they're noise-like signals. Video filter doesn't do that. A video filter is a great try-it-and-see sort of control. So we've talked about trace modes. Let's talk about detectors. Now, spectrum analyzer sampling can be very fast. Normally, it produces thousands of sample points per sweep, or even more. We only have so many pixels on the screen. So somehow, we have to take these thousands of sample points and compress it to something that can be displayed on a screen. So there's a variety of ways we can do this, okay? In the picture here, I have 8 samples shown for pixel n. And if I take the highest sample out of this, I'll call that peak detect. If I take the lowest sample of the group, I'll call it negative detect. If I average all the samples, I'll call that RMS. And these are the 3 modes that are most useful for spectrum monitoring. Sample is a legacy mode. It takes a sample at random, and quasi-peak is really for EMC testing. Okay? So what peak can do, peak detect can supercharge your max hold. Instead of having the max hold over 2, 3, 10, or 20 traces, you can multiply that effect by 8, 10, or 100 times by however many data points are taken for each pixel. In the same way, negative is supercharged min-hold and RMS is a supercharged averaging mode. You can use trace modes and detectors separately or in combination for enhanced effect. So we've talked about trace modes, detectors, and now we're going to talk about sweep modes. These are three separate things. Okay, there's fast and burst mode. These are the two we'll use most for spectrum monitoring. Fast is a quick trace update. It sacrifices some accuracy, but it's a very good utility mode for spectrum monitoring. When I'm setting up for spectrum monitoring, fast is my default sweep mode. Then there's burst. This is essentially a receiver mode for a spectrum analyzer. What happens is when you go into burst mode, the instrument stops sweeping. Now what this does is it limits you to the instrument's IF bandwidth of 15 megahertz, okay? But you're collecting traces at something around 20,000 traces per second. So what burst mode does is it guarantees capture of short signals or burst as short as 200 microseconds, 0.2 milliseconds, 0.00002 seconds. That's a pretty short burst. It can guarantee you capture short things. If you look at the our familiar Wi-Fi signal here on the screenshot, I've gone to 15 megahertz span because I'm in burst mode. But look at that min-hold trace, the blue min-hold trace. It is always up. It never goes down. Every single time we've swept, we've captured a Wi-Fi signal on this, 100% of the time, guaranteed. Okay? Now, performance mode is the most accurate mode, delivers you the most amplitude accuracy. It's not the fastest update. No FFT mode is there. It's useful with a tracking generator. Okay. Then there's amplitude settings. What amplitude, what resolution, what amplitude what reference level, do I set my spectrum analyzer to? And what's an attenuator and why do I need it? A lot of this has to do with where am I, okay? I can tell you from my experience that if I'm picking up signals with an antenna, I very seldom see anything stronger than minus 40 dBm. Minus 30 would be an upper limit. If it's higher than that, I've probably got an antenna inside a transmitter housing or something like that. But take a look at the picture in the upper left. All those transmitter towers, or broadcast towers, AM and FM and TVs and what have you. If there's large signals nearby you, even if they're outside of the span you're looking at, they're still hitting the front end of your receiver. Okay, a spectrum analyzer by nature is a wideband instrument. It's capable of looking at a wide range of frequencies, and it can undoubtedly see the frequencies that those radio transmitters are broadcasting at. If those signals get to the first mixer, if they get to the first active component, they can cause overloads. And those overloads create something called descents. It doesn't matter that it's not visible in your span. It's important that your spectrum analyzer or your receiver have a warning that you're in an overload condition. In the screenshot, that's what the red trace is, and that's what the red warning letters are on the screen. It says you're being overloaded by something, whether it's on your trace or not. How do you deal with this overload? Well, the first thing you might want to do after you've been warned that there's an overload is play with either your attenuation or your reference level. Adjusting your attenuation or reference level a little bit can often get rid of this sort of issue and make sure all the signals you're seeing are legitimate. You may need to turn your preamp off. That'll give you a 10 dB advantage or so. You may be able to take advantage of a spectrum analyzer's band switching. Okay, many spectrum analyzers, the wide bandwidth ones, do band switch, and if the if the powerful signal is out of your current band, it's not going to be affecting the front end of the spectrum analyzer. Antennas. I've had some success with dealing with Yagis that have maybe a 10 or 15 dB of rejection of signals outside of their bandwidth, and that can help a situation like this where you have a marginal input overload. If the input load overload is stronger, you may wish to go to some sort of internal filter. If you take a look at the picture in the lower left, there's that handle there that looks a bit like a Klingon spaceship, and there's a filter there in front of it that looks a little bit like a scout ship. Anritsu has a wide range of external filters for use in the cellular and public safety frequencies. You can select a filter, a passband filter for your own band. It's important that this filter be in front of any active component, in front of any preamp. Otherwise, you still get your distortion. And then in the final analysis, you may need to point your antenna away from the signal source or simply move away from the signal source. I sincerely doubt you'd be able to do any sort of effective spectrum monitoring on the hilltop in the top picture. Now we've touched on antenna choices. I've mentioned I like a Yagi because it's tuned and directional. But let's talk about antenna choices in a little more depth here. First of all, if you're dealing with any sort of transmit-receive system, if there's a tower, it can be real handy to use the receive test port on your tower, whether it's a base station or public safety or whatever your application is. If you can use the tower receive antenna, you're using the antenna pattern, the antenna filtering, the antenna azimuth, the aim of the antenna, and all that's taken care of, and you're seeing the signal, the same signal the receiver is. That'll help a lot. If you're doing wide area monitoring, wideband, a large log periodic can be useful. Regulators often use these at monitoring sites. A mag mount antenna is great if you're in a car and doing mobile monitoring. A handheld antenna can be great if you're on foot. Yagi is a good choice because it's band selective. That front-to-back ratio, a good front-to-back ratio is very helpful if you're trying to decide if you're looking at an echo or the true signal. Directionality is helpful on those Yagis as well. A small log periodic reduces the number of antennas you need to carry, but they're also a bit less directional and less band selective than a Yagi. If you're below 500 megahertz, either a Yagi or a log periodic get to be rather large and unwieldy for carrying around by hand, and that's where a loop antenna becomes handy. Then there's the rubber duck antenna. I use it. I'm sure every one of you use a rubber duck antenna on your spectrum analyzer from time to time. They're so small, they're compact, they're mobile, they're so handy. Spectrum analyzers are very sensitive. They can pick up signals as low as minus 160 dBm. That's not very many watts. That's nanowatts or picowatts. And where is the closest RF source? Where is the closest piece of electronic equipment? It's your spectrum analyzer, right? Your antenna's on that spectrum analyzer. All electronic instrumentation has some form of emissions, even if they're well shielded. And your spectrum analyzer, whatever the brand, is going to have some sort of emissions. So there's two ways you can deal with this. One is simply be aware that a small signal you're seeing on the spectrum analyzer can be coming from the spectrum analyzer itself through the antenna. And if that signal doesn't change as you move around, that's a clue. Okay, the other fix is to move the antenna away from the equipment. A few feet is enough. Simply put the antenna in your backpack or on the end of a BNC cable or something like that. That generally takes care of this. If you're doing spectrum monitoring, it's very, very useful to be able to control your instrument remotely. If you traditionally, what people will do is they'll leave a spectrum analyzer at a site, they'll have it set up to record signals, and they'll come back in a week and see what they've got. That can be tedious, time-consuming, and if your span wasn't set up right, you may have to do it again. That's a lot of trips to the site and a lot of back and forth, and it can take a while to resolve whatever problem caused you to monitor spectrum in the first place. If there's Ethernet access. If there's an internet port at the site, it can be much, much handier to set yourself up with an Ethernet connection and remotely control this thing. The Anritsu spectrum analyzers have the capability to broadcast web pages at their IP address. And these web pages can be interpreted by either a Chrome or a Firefox browser. And you can be using your Android mobile phone, your iPhone, a tablet, or a Windows laptop, or really whatever that has a good browser in it to control your instrument remotely. This can even work through a Wi-Fi link. We have an application note detailing that set up, and I'll talk about that a bit later. Then let's talk about trace management. The question here is, how many traces are we going to collect, and how many traces do we want to deal with? When I talk to people about spectrum monitoring, one of the first responses I generally get is, I want as fast as trace update rate as I can get so I don't miss any data. If something comes up for just a second, I want to see it. A little bit of math shows that if I collect 1 trace per second for 30 days, that's 2.5 million traces, or 100 gigabyte of data, with our trace size of 500 kilobytes. That's a lot of data. You're running into, where am I going to store all this? You're running into, how am I going to move all this around? And you're running into problems with, what do I do with all this data anyway? Do I really want to look at 2.5 million traces on my computer? So let's go back and think about how we can maybe reduce that some, okay? First of all, there's time resolution. Why do I want time resolution? I want to be able to capture short signals. Now, if that's the case, there are some alternatives, okay? First of all, max hold records maximum excursions. If we combine that with peak detect, that supercharges max hold, and then burst detect, which spots very short signals, I can guarantee you that over a given period of time, I will capture any short burst that shows up. This means I can use my trace update rate as time of day resolution. I can use my max hold, peak detect, burst detect combination as, I guarantee you I'll show you anything short. It's something to consider. And then there's save on event. Save on event is about saving traces that matter. The simplest form of save on event is save on sweep complete. This is the save everything option. Save on mask violation. Anritsu spectrum analyzers can create a mask. In this case, the green line with the circles on it is a mask that was created based on the max hold trace, then given an offset. Any violation from that mask will cause a save, and then you can examine the spectrum that was saved. This will certainly reduce your data to the traces you care about, if your mask is right. There's also a save and stop for when one mask violation matters. Now, what do you do with all these save on event traces? It turns out that there's a PC application called Master Software Tools, or MST, and it has something called folder spectrogram. This allows you to combine the results of all these save on event data captures into one large folder spectrogram. It'll handle up to 15,000 traces in one spectrogram. At full speed, this is something like 4 hours. Or if we make it 1 minute per trace, this is something like 10 days, to give you an idea of what this will handle. Trade-offs: save on events, relatively simple to use. You can reduce your data with an event mask trigger. Disadvantages: the update rate's not the fastest because you have to save after every single trigger, and that takes roughly a second. Then there's spectrum recording. Spectrum recording can be used for large-scale data reduction. And what you can do here is you can set the parameters, how long you want to record, seconds, minutes, or hours, how often you want the trace to update rate. Use this for your time of day resolution. You can set your trace mode up so you can have a max hold, and you can also have the peak detect and the burst detect if you want it in your sweep mode. So then what you get here is you've got spectrograms happening, let's say, every minute. That's what I did here. And every minute is a max hold of some burst detected trace. And you'll know the time of day, and you know the signal, and you won't have that much to deal with. Master software tools can combine these spectrogram recordings into one big spectrogram. That's really going to help you dealing with these signals. Trade-offs of a spectrogram? Well, for the advantages, a spectrogram is the fastest possible way to get good time resolution. It's relatively simple to use. It works well with that max hold and burst detect. They can be combined. Successive continuous spectrograms can be combined in master software tools so you can analyze things. Disadvantages, well, none of this is triggered. It's all timed. So you could end up with a large data set, and there is a 3-day limit on the recording time. So let's leave data reduction aside for a minute. I'm going to now assume that we have a signal. It's live. It's coming in. I may want to do a little bit of signal analysis on this, a step towards identifying the signal. Now, spectrum analyzers traditionally have a zero span. And what you can do this for, it's a graph. It's time on the horizontal axis and power on the vertical axis. The frequency is restricted to the current center frequency of the resolution bandwidth filter, okay? And you can use this to look at the behavior of signals over time. On the top, we have an FSK signal that's turning on and off. On the bottom, we have a WiMAX signal, a Wi-Fi signal, excuse me. And you can see its action over time. You can measure the time burst information because markers work in time and power. This helps you get an idea of what you're looking at. Spectrum analyzers also traditionally demodulate signals. The analog demodulations are AM, FM, single sideband, upper sideband, and lower sideband. And this will help you listen for station ID. If it's a voice station of some sort, you can pick it up and listen for this is station KQAD to find out who you're listening to. Or some signals like FSK or VOR have Morse code identifiers you can listen to. This is quite helpful if you're dealing with, say, a harmonic of the original signal or an IM product resulting from the original signal. Now let's talk about how we can automate some of this. Obviously, if we're going to be monitoring signals, we don't want to have to pay attention to it day in and day out. The first thing we can do is we can set up with a channel scanner. Now, a channel scanner is measuring true RMS power for its channels. It has some great advantages in that you define the channels. They don't have to be contiguous. They can be separate and discrete channels, and each channel can have an individual bandwidth, whatever bandwidth you tell it to have. And you'll be measuring power in all of these channels. It's also got a very fast update rate. The disadvantage? Well, you aren't seeing a trace. You're seeing channel power, so an unusual shape signal may not stand out, and there's no easy way to view results over time. There's a spurious emission utility, okay? Now, what this spurious emission utility does, it allows you to go to a certain span and center frequency, take a trace, judge it against a limit line, move to another one, span and center frequency, take another trace, judge that against a span and a limit line, and so on and so forth, for as long as you have it set up. And you can see on the screen here, on the screenshot, in the lower right-hand corner, there's some green letters there. Those are saying pass right now. That means we ran a set of spans and center frequencies and nothing violated the limit line we gave it. This has the advantage, it has pass-fail judgment to make some of your decisions simple. It saves a trace for later review. It saves images for later review. And it can be used to automatically check a set of spans. Disadvantages? It's not that fast, okay? It takes about 20 seconds to do one span, unlike the channel scanner, which is very quick. But you do get that picture and you do get the pass-fail. Then there's Easy Test Tools. This allows scripting, automation of some common tasks. It has a very simple command set, but one that's powerful. Here's the 4 things it does. It can display a prompt. In other words, it can tell your end user to do something or press a certain button. It can display an image. On the screenshot I've got here, I'm showing an image that was created in PowerPoint being displayed on the instrument display, and the instrument itself is being remotely controlled over the internet. Okay? It can recall a setup. So if you have some predefined setups, this is how you EasyTest tool can cause the instrument to go to a certain state, and it can save a trace. It can run remotely or in person, and it's a way of simplifying a lot of common tasks. Trade-offs: EasyTest is very flexible. It can be usable with all trace types. It's a spectrum analyzer tool or a cable and antenna analyzer tool. EasyTest files themselves can be emailed to remote locations because each EasyTest file, ETT file, contains all the necessary setups, the images, and the instructions for the instrument all in one file. Disadvantages: you've got to do some advanced planning here, and it's not that fast between setups. So remote control, I promised you we'd come back to this a little bit. So the Anritsu Spectrum Analyzer, currently the MS2720T, do have remote, full interactive remote control using your browser, either Chrome or Firefox. If you hook your laptop up to the instrument through the internet, through an Ethernet port, you can download files, you can log in, you can control the instrument, you can change modes. All this makes spectrum monitoring much, much simpler because I mentioned before there's certain trade-offs in your span and RBW selection. And you may wish to change those depending on what you're seeing out there. If you can save yourself a trip or 2 or 3 or 10 out to your monitoring site, this can be very worthwhile. It does require some sort of Ethernet link between your controlling device and the instrument. This can be a wired Ethernet, or for a short distance, it could be a Wi-Fi link. There's a lot of details on how to set this up in an application note that's available on the Anritsu website. The title of that app note is Anritsu Spectrum Master with Web Remote Tools. So you may want to check that out. So if we're going to use a spectrum analyzer for remote control for monitoring spectrum, we might want to take a look at what we'd want to see in this spectrum analyzer. From my point of view, the first thing I'd look for is full remote control. It makes spectrum monitoring so much easier if I don't have to keep going back to the site to adjust my instrument or see what I've got. On the user interface, there's a wide variety of user interfaces out there. Some of them are easier to learn than others. If you're already a spectrum analyzer user, I would recommend an interface that resembles the other spectrum analyzers out there. Not only will it be easy for you to learn, it'll be easy for anybody working with you to learn. It's very important to be able to record spectrum. If your instrument doesn't have some sort of save or record capability, you're going to end up watching a lot of traces while you're waiting for your signal to show up. A multi-step attenuator is important. If you're in a situation where you may be getting an input overload from some strong nearby signal, it's important to be able to adjust your attenuator in small steps until the problem goes away, because the more attenuation you get, or the higher you move your reference level, the higher your noise floor goes. Okay? A preamplifier, a full band preamplifier, is important if you're dealing with weak signals. I've heard some people say, well, the signal's weak, I don't care about it. Well, you've got to remember the signal that's weak where you are may be strong somewhere else. So if you're looking for that sort of issue, a sensitive instrument with a preamplifier is important. A video bandwidth control is important if you're getting weak digitally modulated signals. Now there's dynamic range. Dynamic range is probably one of the most abused specs in the RF industry. The way I'm going to talk about dynamic range is this is a number that says how well I can view a weak signal in the presence of a strong signal. Okay, in this case, a good dynamic range might be greater than 106 dB in a 1 Hertz RBW. There is another dynamic range specification that says I have one signal, and what's the strongest it can be, and what's the smallest this one signal can be. I'm talking about the dynamic range that's saying how small of a signal can I see when there's a strong signal on my screen. Two very different number sets, okay? One is going to be in the 100 dB range if it's good. The other could be in the 200 dB range. That's how you spot them. Then there's displayed average noise level. In any given span in RBW, you're going to have a certain noise floor. The lower your displayed average noise level, the lower that noise floor is, and the better you can see weak signals. A good number here would be lower than minus 160 dBm in a 1 Hertz RBW. Third order intercept is a measure of how well the spectrum analyzer deals with distortion products. A good TOI means fewer false signals. A good number here is 15 to 20 dB with 2 minus 20 dBm tones and no attenuation. A common way to make this number look better is specify 0 dB tones. Okay? Then there's phase noise. That small mound of noise near the bottom of a large signal. It can hide small real signals near a large signal. Smaller is better. Lower is better. A good phase noise number is better than minus 100 dBc per hertz. And there's field strength measurements. If you're measuring coverage, field strength units and the antenna tables that come with it can save you a lot of calculations afterwards. Field strength units, you're looking for things like watts per meter squared or dB millivolts per meter and similar units to that. So in summary, we monitor it because we're involved in some sort of spectrum clearing regulatory interference or we're looking for capacity. Our task might be to observe and record, or observe and compare. When we're setting our instrument up to monitor, we have to deal with choosing a frequency and a span. We have to deal with selecting a trace mode, a detector, a sweep mode. And all three of those interact together. And then we have to deal with amplitude. And amplitude has a lot to do with what strong signals are nearby, and antenna selection. When we get into trace management, we have to consider how often we really need the analyzer to update. Are we trying to find the shortest possible signal? How many traces do we want? Or do we want time of day resolution with something like burst detect enabled? Will save on event or spectrogram help us out? If we're looking to automate our data gathering, there's channel scanners, there's a spurious emission measurement, and there's easy test tools. And of course, for remote control, web remote control, it's pretty slick to be able to control a spectrum analyzer from your smartphone, I can tell you. As far as specs, we're looking for remote control, a familiar user interface, the ability to record spectrum, a multi-step attenuator preamplifier, and some good specifications. I've given you some sample specifications you can use when you're looking for an instrument of this nature. So that's what I have, and I'd like to open this up for questions now.
Thanks, Tom.
Kyle, are you there?
Yeah, I'm here. We've had a number of questions come in. The first one being, how would you remotely reboot the instrument you talked about?
Okay, if we're remotely rebooting the instrument, and that does need to happen from time to time, what we did on one trial we're working with right now is we have an Ethernet-controlled power switch. The instrument has a mode you can put it into where if you remove the AC power to the instrument, it will power down, and if you give AC power to the instrument, it will power up. That'll accomplish the remote reboot.
Okay, great. Do you recommend a specific Yagi antenna manufacturer?
Eric?
So I wouldn't make a specific recommendation, but I will say that we use some of them for antennas that we sell. Our most common supplier is Telewave. They make very nice antennas. If you look at them, you'll discover they're actually transmit antennas. And the only reason for that we use something that's a little heavier like that is they're much more rugged, to the point where you could even use them as a weapon if you really wanted to. Don't tell the TSA that when you're going through security, however.
All right, thanks, Eric, for those great tips. Anyways, we had some other questions come in, also having to do with the instrument. How would you get the IP address of the instrument?
Okay. The instrument can either get its IP address from a local router. It can get IP addresses by DHCP, or you can set a static IP address. That application note we talked about discusses going either way with that.
All right, great. Thank you. Again, everyone in the audience, please submit your questions if you have them, and we'll try and get to them. Next question coming in. When would someone use a spectrum analyzer versus PIM gear?
So that's a really good question, that they're both useful. We're really talking about spectrum monitoring here. And PIM is a thing that happens when you have complex or multiple transmitters running through a single feed line. So the PIM gear is good to troubleshoot a problem that's going on with the base station. The spectrum monitoring application is really looking for what's going on out in the air, usually from other transmitters. I would say that a fully equipped person would have both sets of gear.
I can say this, that a spectrum analyzer is certainly capable of spotting a PIM problem if it's happening, but the PIM gear will force the problem to happen, so you can troubleshoot it.
All right, great, thanks. Next question we had come in. So for analyzing using your phone, is there a specific app to download, or do they just use the browser on the phone?
If you have a current version of Chrome or Firefox on your phone, you're good. No app is needed.
All right, great, thank you. We had another question about the Yagi. Are there harnesses for the Yagi, or is it cumbersome to use? Do you feel it's cumbersome to use?
So it depends on the size of the Yagi. Smaller ones can be a little bit cumbersome. We actually have an accessory, the MA2700, to help that. Attaches to the Yagi, is got a sling for holding. There's a preamp built in, as well as a GPS receiver and an electronic compass, and even a trigger for helping you get bearings.
Perfect. Thank you, Eric. We had a question about baselines you mentioned. Can you just talk a little bit about what baselines actually are?
What a baseline is when you record spectrums at a certain location for a certain period of time, say 24 hours. And that gives you a good idea of what's happening in your sample period. And then you come back in a month later and compare these baseline traces to what you're seeing now, possibly by doing a difference trace between what's coming in and your baseline, and you can see exactly what's changed. In the case of a difference trace, any new signals, it'll show up flat if everything's the same. Any new signals will show up as a positive move in the trace. Any signals that are missing will show up as a negative deflection in the trace.
All right, great. So kind of a related question. How long can one actually record a spectrogram for?
Well, that's a fairly complicated question, because there are several different ways to get a spectrogram. So the simple answer is, in the instrument, in the interference analysis mode, the maximum you can normally set that is 3 days. However, if you save on event, and if you maybe hook up an external disk drive, it can go for months. Maybe you only have one trace that exceeds a mask that's maybe every day, and you can go on for a very long time. So I have a joke with my wife that the correct answer to any non-trivial question is, it depends. And I think that question fits in this category.
All right, great stuff. So next, do either of you guys have any tips on how to make data acquisition, such as from the internal stored data, easier, specifically transferring to a laptop for processing?
One of the neatest things about the web remote control of our instruments is once you get into that browser, there's a file download tab. And that tab allows you to click on a directory or a group of directories and files, hit the download button, everything gets zipped on the instrument and downloaded to your browser. At that point, it's available with however your browser handles downloads, and you can deal with it from there.
All right, thanks. So you mentioned earlier that the Spectrum will save mask violation. Does that mean the Spectrum has loaded the masks for different technologies and channels?
It'll load whatever mask you create.
All right.
And we give you some tools in the instrument to make creating these masks easier, but they aren't predefined masks.
All right, great. Next question we had come in. Assuming a 5 meg wide UMTS carrier, how do you distinguish between normal variable mobile traffic and interference? It looks like a Bart's head regardless.
So normally you're looking for interference on the uplink, because uplink interference can take out an entire sector versus downlink interference. It tends to be very localized. So uplink traffic tends to be bursty. That's to save the battery in the UE or phone. Because it's bursty, you can use min-hold in the spectrum analyzer. As the bursts come and go, they basically disappear, and then any constant signal, like a CW carrier, will become very visible.
All right, great. Next question we had come in. What if the place one needs to monitor has flaky power?
If there's flaky power, well, that's a real good time to have a battery backup. We were dealing with a situation just like that recently at a public safety site, and they had some flaky power issues. The things that saved us were, number one, was the ability to reboot remotely, and number two was they decided all their equipment had better be powered off their battery bank, their 48-volt battery bank.
All right, perfect. We have time for a few more questions here. So can you use a spectrum analyzer to find PIM issues that are caused by multiple frequencies being combined in one line?
Absolutely, you can. Spectrum Analyzer for years has been the tool of choice for finding intermodulation or PIM issues. The tricky part about using the Spectrum Analyzer for hunting PIM is that currently the current generations of base stations have active power control. That means you don't have control directly of the power they're putting out, and PIM is a power-sensitive fault. So PIM will show up during rush hour or when the call volume is high and not show up at other times, or perhaps it shows up when the weather changes a connection or something like this. The Spectrum Analyzer can spot it, but the PIM gear can force it to happen. And that's the difference between the two.
Yeah, the way I put that in short is that the Spectrum Analyzer gives you a good indication of PIM, but the PIM gear gives you a measurement of PIM. It gives you an actual value that you can have a threshold for.
Okay, yeah, that makes sense. So we had a question from an audience member that just recently purchased Anritsu model MT8220T. Is remote access included in the interference analyzer option, or is it a separate option?
That's standard with the instrument with the next firmware release. It hasn't been officially released on that product yet. Sometime in the next 6 months, there'll be a firmware release that includes that.
Great. So you talked earlier about the telewave antenna. If you had a choice of antenna, would that be it, or are there other ones?
So all antennas are trade-offs. The telewave antennas I like for Yagis when I'm looking at, say, cellular bands. They have high gain, narrow beam width, and good front-to-back ratio. But if I'm looking at many frequencies, I might need to have many antennas. If I wanted to look over a broad range and I was willing to make some trade-offs in, say, the gain or front-to-back ratio, I might use a log periodic antenna or a biblade antenna. We have one of those we sell, for example.
All right, great. Looks like we have time for just about 2 questions left. Can you connect the spectrum analyzer to RF tower ANT to do measurements?
Absolutely. That's the preferred way to monitor is check to the RF tower's receive test port, which is a signal coming from your RX antenna.
All right. So I think we have time for just one more question. Does Anritsu have audio alarms when certain conditions are met or when there is interference?
So the save on event function, for example, every time a trace is saved, you get a beep. So if you have it set up to be save on event when limit exceeded, you'll get a beep every time the limit is exceeded.
All right, perfect. All right, that's about all the time we have today. I want to thank everyone for attending Spectrum Monitoring Techniques, Capturing Unknown RF Signals, presented by Anritsu. Again, today our presenter was Tom Elliott, Senior Product Manager at Anritsu, and helping out with the question and answer section was Eric Hokinson, Senior Product Manager at Anritsu. Thank you, everyone.